Good morning, guys. 9 a.m. and we can start moving. So, in the previous class, we started discussing magnetism. Basically, started solving problems about magnetism, and we solved a few problems, actually two problems, connected to a magnetic fields produced by a infinitely long straight wire. Right, and we use that formula mu naught I divided by 2 pi r. So now let's look at more complicated situation, right? So let's assume that we have a wire, but which is not straight, right? You see, we have a loop of a complicated shape, right? We have two semicircles, right? With radii are given, right? So R1 and R2, and the numbers are given, right? And the value of the current flowing through this loop is also given, right? So we started. I started introducing this problem in the previous class, but just introduced it, right? And today we're going to solve it. So, uh, and we need to find magnetic field. Of course, this current by its nature can produce magnetic field. So pretty much the whole space will be filled with magnetic field produced by this loop. But we need to find magnetic field only at this point at the center, right? Because it's the easiest point, because there are lots of symmetry of the system relative to this point. So it will be reasonably easy to find it, right? To find the magnetic field, right? And so of course, that formula, which we used for an infinitely long straight wire, B equals mu naught times I divided by 2 pi r, is not applicable here, because this is not a straight wire and not an infinitely long, right? So what does it mean? It means that we need to go back to the roots, to the Biot-Savart law in its original form, right? Which allows us to find magnetic field dB produced by an infinitesimally small section ds. And obviously we will have to integrate, because this is not an infinitesimally short section of the loop, right? I mean, not infinitesimally short section. We have a finite loop, right? So of course we will have to go through the integration, right? So let's start moving, right? Pretty much nothing else to tell that, except for we need to diligently apply this formula. And maybe you know what? Let me remind the meaning of each parameter in this formula. Constant current is given, ds. Again, it's infinitesimally short section, infinitesimally small section of a wire, ds. And direction of ds, you see, it's written as a vector, is determined by the direction of the current. Sometimes students forget about that. So current gives us direction of ds. Then r hat, it's a unit vector, magnitude of which is 1, right? And it shows just a direction from the section ds to the point where we want to find magnetic field. It shows, okay, we need to find magnetic field in that direction or that direction. Pretty much it gives us only a direction. Then r squared, okay, r, it's a distance from this section to the point where you want to find magnetic field, right? We discussed that, I reviewed that in the previous class. Okay, so now back to the problem. Since we will have to find a magnetic field which is a vector, and I want to have the final answer in terms of unit vectors. So let me introduce coordinate system, right? We have to introduce. Of course, you can write answer in terms of in or out or right, left, right, in these words, but I prefer to use a coordinate system. All right, which one I picked? Okay, let me choose this coordinate system. Z-axis is into the board, so that is Z, right? And X is up and Y is to the left, right? So I picked this coordinate system. Again, you remember we have constitutional freedom to choose any coordinate system we want, okay? I want this. Okay, and after this, yeah, as I said, we will have to integrate. And obviously we'll have to split this loop into 4 sections, right? Obviously, because it will be nice, reasonably easy integrate over a loop. I mean, semicircle, then semicircle, and then along this straight piece of wire and this straight piece of wire, right? So we'll have to split into 4 sections. And I'm going to divide that into using these points. Okay, let's call this point as point A, this will be point B, all right? And this section will be my section number 1, semicircle. Then let me denote this point as C and this point as D, and then this semicircle will be my section number 2. So first we will take care of 1, then 2, and then this straight piece and this straight piece. So this will be my section number 3, and this will be my section number 4. All right? So as a result, as I said, we first we will have to find contribution to the magnetic field at this point produced by this semicircle. So let me call it B1. So B net will be equal to B1, again, as I said, magnetic field produced by this semicircle at point P. So B1 plus B2, magnetic field produced by this semicircle, plus magnetic field produced by this section at the point P, so it will be B3 and plus B4. Okay, naturally we split into 4 sub-problems. We split this problem into 4 sub-problems. Okay, and now one by one. Let's start with B1, then B2, then B3, and B4, and then at the end we add up all those contributions. Right, so let's start with, okay, let me put a small bullet. Let's start with B1. First section, from A to B. All right, okay. Magnetic field is a vector, right? So it has magnitude and direction. And let me start with a direction first. Let me first find direction of B1 at this point. Right? And what determines the direction of magnetic field in this formula? I mentioned that in the previous class, and now I need to remind you, direction is in this cross product, ds cross r. These are just numbers, just constants, right? Direction is in ds cross r. So let's look at that ds cross r, right? So first, let me take care of the direction, right? So, and as I said, direction is in d. Okay, let me write ds cross r hat, right? So I just rewrote over here just to take care of that. Okay, let's draw it on a picture. ds1, okay, it's a small section in the first semicircle. Let me draw it here, for example. Let me take this point, and you remember direction of ds. Direction of ds is determined by the direction of the current, right? And again, it's a infinitesimally small section, so it will be tangential pointing that way, because direction of the current, you see, that way. So this will be my ds. Okay, ds1, right? You see that? ds1. Maybe I can make it slightly longer. Right. Of course, I exaggerated. It's infinitesimally short. ds1. Then, what is r hat? You remember a few minutes ago I told you the meaning of r hat. It shows a direction, and it points from segment ds to the point where we want to find magnetic field. So ds, our ds is here, point where we want to find magnetic field here. So r should point to our point P. Right? So this will be, which should color I use? Right. Okay, let me first draw. This will be r small, and r hat, this, okay, let me use, since it's kind of important, let me use red. So this will be our r hat. Again, I said, by definition in this formula, r hat, it shows the direction from ds, you see, from ds to the point where we want to find magnetic field. All right? Okay, so now, right-hand rule. In order to find the direction of the cross product, right-hand rule number 1. So first you need to align your hand along the first vector in the cross product, so it will be that way, right? Then I need to orient my hand in such a way so that I can naturally bend my fingers in the direction of the second vector in the cross product, and r hat is towards the center, towards the point. So it will be ds cross r. So you see, my thumb gives me a direction of the cross product. So it is into the board, into the board, into the screen. ds cross r. Right. So into the page. So in this case, it's into into the board. Into the board. So which is in terms of our coordinate system, into the board plus z direction. So of course, b1 will be equal. So b1 will be equal to absolute value n times plus z hat direction. Okay, so now we know a direction. So now we need to find the absolute value of magnetic field b1. So now we just need to integrate properly. So now magnitude. Right. Okay, so now, yeah, we need to start integrating. So b1, okay, that's the absolute value. And now I'm finding this b1, right? Of course, it will be integral. From which point to which point? That's our beginning of the first section, and that's the end. So from A to B, and I need to rewrite that mu naught times I divided by 4 pi. Then we are finding magnitude. We know the direction. So over here, I can put an absolute value sign over ds cross r, which just tells us we need to find the magnitude of this cross product, right? Because direction we already found. So I can put an absolute value on ds cross r hat and divided by r squared. So that's the integral which we have to take. First, it looks scary, right? But it's not. I will show you. First of all, mu naught I over 4 pi, these are just constants. We can take them out outside of the integral. And again, strictly speaking, yeah, it's a calculus 3, it's an integration over a line, but we're going to integrate it without actually integrating it. But we have to justify everything. Okay, let me open my explanation box and take care of these pieces. What about r? R, what is r? It's a distance from ds to the point in question, to the point where we want to find magnetic field. Do we know that distance? It's r1 because we are on this semicircle, right? And it doesn't matter which ds you take during the integration. Over here, over there, this, all the way to point B, to the point B. R is constant, r1. R equals to r1 all the time in this integral. So immediately I can write that r equals to r1. It's a constant. We should be able to take it outside of the integral without any troubles. Now let's take care of this absolute value. All right, so ds1 cross r hat. Of course, by definition, cross product, right? Previous, 2 lectures ago, right? We reviewed the absolute value, reviewed the cross product. It's absolute value of ds1, absolute value of r hat, and times what? Sine of the angle between them. Sine of theta. And let's look carefully. What is this angle? What's the value of this angle? Theta. It's the angle between ds and r hat. Look at the picture. Direction of ds, it's a tangential to this loop. I mean, not to the loop, to the semicircle. To the semicircle, tangential direction. Direction of r hat, straight radial. What's the angle between the, where is my loop? Here. What's the angle between tangential direction and radial direction? We all know the angle is 90 degrees. Property of a circle, right? So this is 90 degrees. All right. Then what's the absolute value of r hat? 1. So what's left effectively? And of course, the sine of 90 degrees, again, it's 1. As a result, what's left? Only absolute value of ds1. Okay, so now I will just drop that and write just the ds1. Yeah, we can also write down absolute value of the vector like this, right? So that's what's left from this scary construction. Okay, so now I can close my explanation box and continue this line over here. So all these constants can be taken outside. So it will be mu naught times I divided by 4 pi and r squared. It's r1 to the power of 2 and integral from a to b of ds1. Again, still, it's a complicated integral, right? You will learn how to do this integration in calculus 3, but your high school knowledge is enough to know the answer. What's the answer? What's the value of this integral? What's the meaning of this integral? You just take small ds, basically small length, plus small ds, plus small ds, plus, and you keep adding these small ds's until you move from point A to all the way to point B. Of course, it will give you this total distance, half over circumference, right? Half of the circumference, 2 pi r divided by 2, it's a pi r. Of course, everyone knows that, right? So the value of this integral is pi, and of course r1, because the radius of the that is r1, right? Okay, so now you see that? Because sometimes students don't see why pi r, because it's a semicircle. The circumference of the whole circle is of course 2 pi r, but we have only half of that, so pi r, right? Okay, so now of course this pi and that pi can be cancelled. R1 and 1r1 over here also can be cancelled. As a result, we'll have mu naught times I divided by 4 times r1. All right, so that's the absolute value. You see, at the very beginning, yes, the integral looks so scary, kind of, oh my god, what I'm going to do, right? But once you start diving, you realize, damn it, it's actually a trivial integral. But of course, you need to know the meaning of each element in the formula, right? Okay, so now of course, the final answer for the B1 absolute value, okay, not the absolute value, just B1. It will be this, mu naught times I divided by 4 times R1, and in the plus z hat direction. So that's the contribution to the final answer from the first semicircle. All right. Now let's do exactly the same for the second semicircle. And of course, your gut's feeling should tell you it will be very, very similar. Very similar. Okay, let me do it now for B2. All right, again, let me start first with a direction. Okay, let me start here with direction. Again, so it's a, but now I will put ds2 times, cross r hat. All right, and again, let's draw it on the picture. Let's see where are these elements. All right, so ds2. Okay, now we are on this semicircle. So ds2, okay, let me draw it here. Oops. All right, so this is my ds2, right? Then r distance, of course, from ds to the point in question, and r hat also points that direction, in that direction. So this will be my r, and okay, r small, and r hat, this is r hat, right? And you know what, I should have also shown that over here this angle theta is 90 degrees, right? 90 degrees, right? I discussed that over here, right? But didn't show it on the picture. Okay, so now ds2 cross r. And you know what? I should have also shown the direction of B1 over here. So B1 is cross B1. Okay. So now back to this cross product. ds2 cross r hat. ds2. Again, right-hand rule number 1. ds2 that way. So I need to align my hand along that direction. Then I need to orient in such a way so that I can bend my fingers in the direction of r hat, because that's the second vector in the cross product. So ds cross r, my thumb gives me direction of the cross product out of the board, out of the screen, right? Out. So, which way I wrote? Okay, out of the board, right? Basically, in a minus z hat direction out of the board, it's a negative z direction because I picked z axis into the board, right? Okay, so I can write that b2 vector equals to absolute value of b2 and minus z hat direction. So now we just need to take care of the magnitude. The same, you see, steps very similar. So magnitude, right? And I need to write a similar integral. So b2 equals to integration from what? We start from point C and move all the way to point D. From C to D. And the same, I just need to rewrite BS law over here. Biot-Savart law, of course, right? 4 pi, then again, absolute value, because now we know the direction. So now we just need to write down the absolute value of the cross product. ds2 cross r hat divided by r squared. Again, it's just a complicated construction. Biot-Savart law doesn't look very elegant. It looks very kind of clumsy, right? Lots of different things. All right. Again, explanation box. R. What is the value of r? Again, it doesn't matter where you are during the integration. R equals to R2 because we're in a semicircle. R equals to R2. And then absolute value of ds2 cross r hat. In a similar way, it will be just absolute value of ds2. Again, it's absolute value of ds2 times absolute value of r hat and sine of 90 degrees, because again, this is the angle between the tangential direction and the radial direction, 90 degrees, right? So it will be equal to just ds2, right? Okay, so constants can be taken outside. 4 pi, then r squared, again, it's r capital. R sub 2, again, can be taken outside of this sign of the integral. And integral from C to D, ds2. Right? Okay, so the same question. What's the value of this integral? Again, in calculus 3, you will integrate this. Of course, you will derive, but we know the answer. So half as a circumference. It's a pi, but now it's r2, of course. Pi r2 again. Pi pi cancels. 1 r2 also cancels. Right. As a result, we're getting the same. Okay, similar. Mu naught I divided by 4 r2. Right. Okay, so now, of course, I can write contribution b2 like here. Right. It will be mu naught times I divided by 4 r2 and in minus z hat direction. So that's contribution to the net magnetic field from the second semicircle. Now, what's next? Section 3. Okay, this is first bullet, second bullet. Now I need to write the third bullet. What will be the contribution from the sections 3? And you know what? Over here, every time, first I started with direction, then magnitude. But now let me start with the magnitude immediately. And in a few minutes, you will see the reason why I wanted to start with magnitude. All right, so let me start with magnitude immediately, right? So of course it will be B3 equals to integral, and again I will rewrite Biot-Savart law, our BS law, right? So it will be, but of course integration from what to what? Section 3, from point B to point C, from point B to point C, and it will be mu naught I over 4 pi, and again just the magnitude. Again, I will put an absolute value sign on ds3 cross r hat divided by r to the power of 2. And let me open the explanation box. And let's look at the cross product. Explanation box. So it will be absolute value of d3 cross r hat, absolute value of ds3. You know what? Let me show ds3 on the picture. First I thought writing it down, but yeah, it's better to show it immediately, right? So let's see on the picture. ds3. Again, it will be infinitesimally small section over here. And again, you remember what determines the direction of ds? Direction of the current. I told you already several times, right? So it means that ds3, it's this way, right? So you see the small vector ds3, and of course points that way because that's the direction of the current in this small section. Then what about r hat? R hat, again, you remember r hat, it shows a direction from ds to the point where we want to find magnetic field. In this case, ds is here, point where we want to find magnetic field is over here. So r hat will point that way, or points that way. So this will be our r hat. So they are in opposite directions. ds that way, r hat this way. What's the angle between them? 180 degrees. So let me write that down now. So r hat absolute value and times sine of 180 degrees. What's the value of sine of 180? 0. As a result, it's 0, the cross product. Let me all close my explanation box. And so this is 0. It means the whole integral is 0. That's why I didn't start with the direction, because what's the direction of the 0 vector? All right. Okay, so I can write, so B3 equals to 0. The contribution from the third section, there's no contribution, right? Good. Now the last section, this one. And probably somewhere inside, you should get the feeling what will be the answer. But anyway, let me put a new bullet, and B4. Similar like B3. Let me start with the magnitude. So B4, it will be integral of, from what? From point D to point A. From D to A. And let me again just rewrite Biot-Savart law. Absolute value of ds4 cross r hat divided by r to the power of 2. Again, explanation box. And let me do similar manipulations. Let me look at the absolute value of this cross product. ds4 cross r hat, right? Okay. Let me draw it on the picture, ds and r hat. Again, ds, the direction of ds is determined by the direction of the current. So current flows from D to A, right, that way. So that's the direction of ds. Right, okay, let me draw it this way. So this will be our ds, right? So ds points that way, because that's the direction of the current. Then, what about, okay, I can make it longer. Right. Then direction of r hat. Again, r gives us a direction from ds to the point in question, to the point where we want to find magnetic field. ds here, point there. So r hat also that way. Let me draw it slightly underneath. So this will be our r hat. What's the angle between them? Two parallel vectors. The angle between them is 0. So I can write as a result, so it will be ds4 times r hat times absolute value of r hat and sine of 0 degrees. Sine of 0 degrees is 0. So the value of the cross product is 0. The whole integral is 0. So contribution from B4 is 0. From the fourth section is 0. Okay, whew. Finally, we took care of all 4 parts, right? So this we just showed is 0. This is also 0. So let's put them all together and we're done. So finally, B net equals, you know what, we found B2, but I didn't show it on the picture. Let me just add. So B2 direction, of course, will be represented by the dot because it's out of the page, right over here, out of the board. Right. Okay. So it will be B1 plus B2. B1 is this, mu naught times I divided by 4R1. Current, of course, the same because we have a loop. Of course, the same current will be in every section. Then direction is plus z hat. And then where it might be 2 here, mu naught times I divided by 4R2 and in minus z hat direction. Okay? We can factor out a few things. Mu naught times I common are 4. Then z hat I can also take outside. And what will be inside? 1 over R1 in the brackets and minus 1 over R2. Of course, R's must be in meters, right? Don't forget to convert to meters. Right. Okay, so now what will be the answer? Maybe I will emphasize. So these must be in meters. Don't forget. Right. And so as a result, we can write, so B net will be equal in a positive z direction. And the answer, the absolute value is, okay, 7.9 times 10 to the power of negative 5 units of Tesla. So the net magnetic field is in the positive z direction. And that's why actually I knew from the very beginning, so that's why I picked z-axis into the board. Right. But again, if you pick z-axis in the opposite direction, again, it's not a crime. You have freedom to choose any coordinate system you want. Right. So that's the answer. In your homework, there will be a somewhat similar problem, but instead of 2 semicircles, you're going to have a small arc length over here. I think they're subtended by the angle of 60 degrees. And this wire, this part, will go to infinity. Pretty much there wouldn't be contribution from this section. All right, so the only difference, it will be very, very similar over here when you evaluate the integral. Of course, you're not going to have half of a semicircle. Circumference, half of its circumference. You will have to, of course, divide 2 pi r by a larger number in order to get the arc length. You will figure it out. And of course, yeah, as I said, this section, it will be sent to infinity. Pretty much there wouldn't be any contribution from that section. Right? Otherwise, very similar situation. Right? This problem is more complicated. So you should be able to handle that problem by yourself in your homework. Okay, so that's this problem, and now Ampere's law.
Okay, Professor, I have a question. I may have missed it, but where does pi go? in the denominator.
Okay, yeah. That question happens. You see over here. Okay, let me. You see the value of this integral is pi r. You see we have pi, and here we have pi. What can we do with those pi's?
Oh, okay. Cancel them out.
Cancel. Yeah, yeah. I heard that question also in before. I think once or twice, right? So yeah, that's why I got immediately right. So, but I thought it's yeah, you just cancel. And of course, one r over here r1, and here r1 to the power of 2. So of course this r and that r1, one r1 will be cancelled, right? So as a result, downstairs we have only first power of r. See that?
Okay, yeah. Thank you.
Yeah, 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 yeah. Okay, good. Now, if you don't have additional questions, then Ampere's law, and let me first review it. Yeah, we wouldn't be able to finish it. Right, so we will finish it most likely on Monday, right? And I will postpone the homework. So let me separate this. So Ampere's law. Right. One of the fundamental laws in physics. And again, as I told you in the lecture, it's one of the equations from the set of Maxwell's equations. And as you know, Maxwell's equations, they form the foundation of the whole electromagnetism, right? Okay, so Ampere's law, let me start with some arbitrary examples. So let's assume that we have 3 wires, right? 1, 2, and 3. Something like this. Right, and let's assume currents. This is up, I1, I2, let's say, is down, and I3, let's say, is up. Right. Completely arbitrary situation. Then, just for fun, let's pick a completely arbitrary loop. Closed loop, of course, right? Maybe something like this. Right. It's sort of like in the lecture. Completely arbitrary closed loop, right? And of course there will be magnetic field created by these currents. So the whole space will be filled with the magnetic field, right? So if you calculate the line integral or linear integral of around this loop, this integral of b dot ds, where ds is an element of this loop, infinitesimally short element of this loop. Again, it's a line integral, light line integral. And again, you see circle in the middle. Circle in the middle means integration is over closed, in this case, closed loop. In the Gauss's law, we had integration over closed surface. Here, closed loop, right? So, and if you calculate this integral over that loop, it will be equal to mu naught, our new universal constant, times the total amount of current enclosed by your chosen closed loop. We can write it I sub in, enclosed, right? And integration is done over that closed loop, and we usually call it Amperian loop. Amperian loop. Okay, properties of this Amperian loop, right? Or maybe I can say which steps we have to make in order to apply Ampere's law. So first, of course, you need to pick an Amperian loop. Which way, right? So first, choose an Amperian loop. And as I told you, it must be closed. It must be a closed loop. If you pick some line which is not closed, it doesn't work. It will not work. Right. So this Amperian loop must be closed, and basically it's an imaginary loop. It doesn't mean that there must be some physical loop. No, no, no. You're just imagining, okay, I want to use this closed loop. Okay, this is my Amperian loop. We did the same with Gaussian surface. It's a mathematical concept, of course, right? Closed, and let me write imaginary. Of course, it's imaginary. So then, second, we need to choose direction of integration. Because whenever you have a loop, and if you start integrating, like over here, every time we integrate it from A to B, from C to D, right? Every time, whenever you integrate, you need to pick a direction, integrate over a line. So this way or that way, basically clockwise or counterclockwise, right? So choose a direction, right? Second, choose a direction, right? Then, once you pick a direction, okay, let's imagine that I picked this direction. Right, so if you look from the top, it will be counterclockwise. Right. Okay, and again, what's the meaning of this integral now? ds, it's like here, right? You see, you pick a ds, for example, this small ds, right? You see this small ds. All right. Then, of course, at that small infinitesimally small ds is basically like a point. There will be, of course, some value of the magnetic field B, right? So you take a dot product of B dot ds dot product. We're familiar with the dot product, scalar product. You will get some number, small contribution to this integral. Then you move to the next ds, small ds. Again, there will be some value of B at that point. Again, take a dot product. You will get second number. Now you have two numbers. You add them up. Then move to the next ds. Again, dot product, B dot ds. Small number, add to the previous two, and so on. You keep moving around this loop, adding these small b dot ds's until you get back to the original point, completing the loop. And when you finish adding all these small b dot ds's, that's the meaning of the integral over a line, over this closed loop. All right. But of course, every time you need to pick a direction. Then, so that's what we have on the left-hand side. Now, the right-hand side, current enclosed. Basically, it's a total amount of current physically embraced by your Amperian loop. In this case, I3 is outside. We're not counting it towards total enclosed current. In this case, we have I1 and I2. And all the time in our problems, all the currents kind of will be parallel to each other or anti-parallel. So there wouldn't be some weird angles, right? All right. So now, then after this, you can take care of the I enclosed. I enclosed, it's a total current. Okay, total amount of current, of course. Enclosed by the Amperian loop. Enclosed by the Amperian loop, okay, in this case. Right. But of course, at the same time now, we obviously see one current is up, the other current is down, enclosed current, right? Again, I3, who cares? It's outside of the borders, right? It's a foreigner, right? But I1 and I2, yeah, they must go into the equation with different signs. And in order to figure out which current is positive or which current must be positive in our equation and which current must be negative, we apply a right-hand rule number 2, the second one basically, right? It's the same rule, just applied in the opposite direction. So once you pick this direction of integration, let's say this, right? So then you, let's say this is our direction, right, that way. So curl your fingers in that direction, and your outstretched thumb gives you direction for a positive current, or positive current direction, right? Again, just curl your finger and outstretched thumb. So in this case, I1 is positive, I2 is negative, right? So then after this, number 4, so we need to apply right-hand rule number 2, right? So in this case, I can try to draw, but usually it looks ugly. 1, 2, 3, 4. Okay, curl fingers. So that's the positive direction. So this is plus I direction, right? So as a result, I1 which we wrote is positive, and I2 is negative. Right. Okay, and so yeah, maybe I should write, so I enclosed equals to I1 minus I2. Okay, that's what we need to do in order to take care of the of this Ampere's law. And now let's look at the example. So how much time? Okay, 5 minutes at least. We will be able to start. Okay, I need that picture. Let me erase this bottom. Okay. So in the lecture yesterday, we started looking at one example. We have a infinitely long wire with radius r, right? And we needed to find magnetic field inside of the wire and outside of the wire. Now let's make a hole in the wire, right? More complicated situation. Right? Okay, I prepared a few pictures. I mean, a few things which can help me to draw a better picture. Right, so let me separate it like this, right? And I think it's a problem 57, right? 2957. 2957. Okay, infinitely long wire with a hole, concentric hole, right? Okay, let me draw it. You see what I have to use? I have to use plates, right? Because of the markers, it's completely black, right? After a year of using it, right? And now it doesn't feel like flat, the plate. Okay, it should be enough. No, let me move it slightly lower. Okay, so that's the outside radius. Now I have to use scotch in order to draw a hole in the wire. Right. Okay, it looks more or less concentric. Oops. So metal is over here. And of course, that's where current is. That is a hole. Maybe I can even try to draw a three-dimensional picture. Okay, so that's our wire, infinitely long. Okay, radii. Inner is B. Okay, let me draw it here. So B, and outer is A. B and A. Okay, maybe let me make it bigger. Right. B and A. Then current is given. Current flows this way. We have a uniform distribution of current. Every time in all the problems, we have uniform distribution of currents in order to make calculus simpler. Right. Okay, so that's the situation. Okay, what is given? Let me write down basically I, A, and B. That's what is given. So we need to find magnetic field everywhere. And let's start with finding magnetic field outside. But before, of course, now you can use two approaches. You can use Biot-Savart law like we did here, right? But application of Biot-Savart law will be quite complicated. It's not worth of troubles. So we have two alternative approaches, either Biot-Savart law or Ampere's law. Here, Ampere's law, it's a piece of cake, right? Okay, not piece of cake, but way, way easier, right? Because of the cylindrical symmetry. Sorry. Okay, so we need to find magnetic field, and in part A, let's find B. Oh, we even didn't finish this. Okay. So first we will have to find B outside, and then outside, let me just write down, where R is larger or equal than A. Right. Okay. So we will finish this example on Monday, because problems like this will be on the exam. So and as a result, the current homework, I think it's number 9, will be postponed till Wednesday. Right. So we will finish this example on Monday.